Welcome to tutorial 12. Today our first task is about the Runge-Kutta second order method, Heun's method. So here we are given a differential equation and an initial condition, and we have to use the Heun's method to determine the approximation of the differential equation at x is equal to 4, and our step size is 0.1, and at the end we have to calculate the absolute relative true error for our answer. So let's get started. Here we have the differential equation and the initial condition written. What we have to find out is y at x is equal to 0.4, and our step size is 0.1. Our function at x comma y is this one here. So this one here is in the format dy by dx is equal to f of x comma y. So we can solve this by using the Heun's method, and so therefore now this function of us at point x comma y will be x times y. So now let's write down our formulas for the Heun's method. So we have here yi plus 1 is equal to yi plus half times k1 plus 1/2 times k2 times h. And then we have for k1, or let me write it side by side. So for k1, the formula is the function at xi yi, and then we have k2, which is the value of the function at xi plus h comma yi plus k1 times h. So now if we place our values that we already know here, we'll have for this one, we'll have here yi plus 1 is equal to yi plus, so here we have 1/2 times k1, so it would be above also k1 here, plus 1/2 times k2 times h. So we know the value of the h already, which is 0.1. Now for k1, we have to find out the function at xi yi. So our f of x comma y is x times y here. So what we can do is we can just take the xi times yi for it. So just replacing these values here by these values here. So we have, instead of the x now xi, and so the y yi. So we have xi times yi, and then for k2 we have f of xi plus h, so h is 0.1 that we know, comma yi plus k1 times h, which is 0.1. So what I've done is I have replaced the values of h and put up the functions. So here we could also write k2 as this term here times this term here, replacing x and y. So it would be x plus 0.1 is the value of the x here. Then we have times, so putting them in the function, right? So here we have the function and taking x and y and putting them in the function here. So we'll have here yi plus, you can say 0.1 times k1. So that would be the value for k1, k2. So we have got formula finalized for k2, formula finalized for k1, and the formula finalized for yi plus 1. So we're going to use this ahead now, and also not to forget, we'll have to find out the values of x I plus 1 using x0 plus I times h. So now let me draw our table. Okay, so first we'll have the values for I here, and then the xi, then we'll have the values for k, and then the values for k2 and yi. So if I write them down, we have here I, xi, k1, k2 and yi. So for I, we'll have, when it's 0, we know that when it's so here this is x0 and this one here is y0. So x0 is 0 and y0 is 1. Now when I is equal to 1, we have for x1 the value will be x0, which is 0, plus 1 times h, 1 times 0.1, which is 0.1. When I is equal to 2, we can just add h to the previous value of x, so 0.1 plus 0.1 is 0.2, and then we have 0. Here I think I drew one row less here, so I would like to redraw the rows again so it's more clear. Okay, so now we have when I is equal to 1, x I is equal to 0.1. When I is equal to 2, we'll have 0.1 plus 0.1, which is 0.2. When I is equal to 3, 0.2 plus 0.1, which is 0.3. And when I is equal to 4, we have 0.3 plus 0.1, 0.4. So we want to find out the value of y at the value of x is equal to 0.4. So that's our last range that we need to reach to. And now we'll work on finding the value of k1. So using our formula here for k1, we have to take the previous xi and yi values, so which basically means x0 times y0 here. So x0 is 0 times y0 is 1. So we have 0 times 1 is equal to 0. And then for k2 now we have x. It's supposed to be xi here, so we'll have here now xi. So basically the previous x, which is x0. So we'll have here x0 plus 0.1 times y0 plus 0.1 times k1. So the k1 value is 0, as we can see here. And then if we solve this, we'll get here x0 is 0, 0 plus 0.1 is 0.1. And then we have y0 is equal to 1, and 1 plus 0.1 times 0 is 0, so 1 plus 0 is 1, and that gives us the value as 0.1 itself. So now to calculate yi or y1, we will have y0 plus half times k1. We can replace the value for k1, or let me write the formula down here. So half times k1 plus half times k2 times h. So y0 is 1 plus half times k1 is 0, so 0 times half is 0, and then we have plus half times k2, so 1 half times k2 times so let's write that down here. We have 1 half times k2, which is 0.1 times h, which is again 0.1. So that will give us the value 1.005. Now if we go to calculate k1 for x2, we will have here x1 times x1 times y1. So x1 now is 0.1 here times y1, what we just got is 1.005. So if you multiply those two, you will get here 0.1005. Okay, now for clarification, I would like to write here, this is x0 times y0. So okay, now to calculate y2, we'll have here x1 plus 0.1 times y1 plus 0.1 times k1. So k1 here is 0.1005. So now this will have here x1 is 0.1, 0.1 plus 0.1 is 0.2 times we have y1 is 1.005 plus we have 0.1 times 0.1005, and when we calculate this here, we'll get the value as 0.20301. Now to calculate the value for y2, we have y1 plus half times k1 plus half times k2 times 0.1 So y1, we know the value is now 1.005, plus we have half times k1, which is 0.1005, plus here we have half times k2, which is 0.20301, and the whole thing multiplied by the h, which is 0.1. So this gives us the value as 1.0201755 here. And then now we'll calculate k1 for x is equal to 0.3. So for that, we'll take the values of x2 times y2 so here we have x2 is 0.2 and y2 is a long number, so 1.0201755 here, and when you multiply them you get the value as 0.2040351. And then now we'll calculate for k2. So we have here x2 plus 0.1 times y2 plus 0.1, or we have the y2 plus 0.1 times k1, so just write here k1. So this here is also not visible well, so y2 and k1 here. So this k1 in k2 always refers to the k1 just before it, right? Just the k1 in its own row. So if the k1 is here, it means this k1 here, this value, and for this part here the k1 is representing this value you can see over here. So k2 is using the value of k1 in the same row. So here now we'll have, if you rewrite this, you have here x2 is 0.2 okay, so x2 is 0.2 plus 0.1, we have 0.3 here, times we have y2, which is 1.0201755, plus we have 0.1 times k1, the value of which is 0.2040351, and this gives us the value 0.312173703. Okay, now here we have y2 plus half times k1 plus half times k2 times h. So y2, as we can see, is 1.0201755 here, plus we have half times k1, which is 0.2040351, plus we have half times, it would not fit in here maybe, so I'll just write it down. So we have here plus half times K2, which is 0.312173703, and then we'll have here times 0.1 for H. So this one here now is equal to 1.04598594001. Okay, 01 or 02, you can say here 02. Now for 0.4, if you calculate here, you will get the value as 0.313695782005, and for this you will get here 0.4309462073418 or 73418, and here you will get 1.0832230396194. So that's the value of, or that's approximately the value of y at 0.4 here. Now let us calculate for the exact value of this. So we have here, so first let me write here that y of 0.4 is actually 1.0832230396194. So I have taken here long decimal numbers here, but you don't need to do that. In examination, either I'll mention you how many decimal places to take, and if not mentioned, then I will say you general how many you should take also. So here now, to go to the exact value, we need to find out the function for this differential equation here. So we have the differential equation that looks like this here. dy by dx is equal to x times y. So what we do is we take the dx to the other side and y to this side here, basically keeping the same terms in one side. So this is called separable differential equations, where you take the same terms to one side here. So we'll take all the y this side here, so we'll have dy by y is equal to x times dx. So we have both the y's this side and the x that side here. So this one can be written as 1 over y dy is equal to x times dx. And then what we do is we find the antiderivative of this. So this one will be ln y, and this one will be x squared divided by 2 plus the constant c. Now if you take ln to the other side, you will have here y is equal to e to the power x squared divided by 2 plus c, which can be written as e to the power x squared divided by 2 times e to the power c. So c is a constant and e is also a constant, and a constant raised to the power of a constant will also be a constant, right? So what we can do is we can say that this constant is, we can just call it a c. So we'll say that y is equal to c times e to the power x squared divided by 2. And now we have given the condition here, initial condition, which is y0 is equal to 1. So if we replace the values here, so y is 1, c constant, e to the power x is 0, 0 squared divided by 2. So you can see that we have c here is equal to 1. And now if we put the value of c into the equation here, we'll get the actual equation, which is y is equal to e to the power x squared divided by 2. So once you get the actual equation here, what we can do is find out the exact value of y at 0.4. So if you put y at 0.4, so you'll have e to the power 0.4 squared divided by 2, and that gives you the value 1.083287068. And now to find out the absolute relative true error, we have the exact value here, which is 1.083287068 minus the approximated value 1.08322. So I won't be able to fit in, just take it more that side here. So we have here 32230396194 divided by the actual value, which is 1.083287068 times 100. So that gives us an error of 0.0059%. And that's the end of task 1.